Alright, welcome back guys to video number 2. In this video we're going to go over the block diagram of our keyboard design and also briefly talk about why we chose the specific microcontroller for this project. So really quick, in the table of contents, because I've already put some work in prior to working on this video series, I'm already more or less expecting to have these pages in our design, right? So we'll have a power page, which is going to be our USB connector, which supplies power to our board, the microcontroller, which we'll talk about in a second. We're then going to have a matrix of key switches in our design. And then finally, we'll also have some LEDs and the LCD portion of the design. So let's take a look at the block diagram. Now, this isn't an exhaustive block diagram. There's going to be some additional peripheral, decoupling capacitors, a crystal required, flash memory, and things like that. But this will kind of give us the idea of what we want this keyboard to do and how we need to make the connectivity possible through the use of, connectors, ICs like a regulator, switches, and so on. So starting from the left, this is kind of the start of our block diagram. This is where our inputs are. Usually the right side of the block diagram is where the outputs are going to be. So we're planning on connecting this keyboard via USB, specifically USB-C. And this will supply our VBus 5-volt power to the board, which we then expect to regulate down to 3.3 volts. Now the USB data is going to go back and forth from the USB connector to our microcontroller of choice. We'll talk about this in a second. We have two choices, at least from my research. These are kind of the most common choices when it comes to creating a custom keyboard. So we have the ATmega 32U4 or the RP2040. So independent of which microcontroller we choose, we will then have a matrix of mechanical key switches, and there will be a lot of different sizes of key switches. And I'll show you guys how we can actually handle that with built-in OrCAD tools, such as alternate symbols, so that we're not forced to create, 15 different switch symbols just because each of them has a different footprint. We'll also have some addressable RGB LEDs. What addressable means is that we can have a chain of these LEDs, so maybe about 12 of these, but they only need a power and a ground pin, as well as a data in and data out, so that you can daisy chain multiple of these LEDs together. And RGB because, well, if we're going to make a mechanical keyboard, let's make sure that it looks good, right? It can blink different colors, maybe diffuse some cool mixture of colors as well. And then finally, we're going to have this 16:2 LCD module. However, because of the limited number of I/O on these microcontrollers, we're going to use an I2C expander. An I2C, if you're not familiar, is actually a two-wire interface, right? So you have your SDA and SCL, which is the data and the clock lines. And this is going to allow us to expand our I/O so that we can, have a 4-bit data mode coming into this LCD so that we can change the display on the LCD to show the numbers. Really quickly, I just want to fix this here. So I2C is a two-way interface, so we expect data to and from the IO expander. However, in this case, we're only sending data from our microcontroller through the expander into our LCD module. Let's talk about which of these microcontrollers we're actually going to choose for our project. And I have here a page 9, which I called an appendix, kind of just going over the pros and cons of the two microcontrollers, which we're going to be considering. So at the top here, I have the RP2040, which is created by, the same company that creates the Raspberry Pi compute modules. And then the ATmega 32U4, which is a microchip component. So starting with the RP2040, there's a couple pros which really stand out to me. First is that the cost is very, very low and that it is also very fast, right? So this chip runs at a screaming 133 megahertz. So if we are worried about, not catching a certain button click or displaying the colors on our LEDs fast enough, well, this one is definitely going to make sure that we can execute our code at a fast enough speed. It has 30 GPIO. The 18 mega 32U4 has 26 GPIO. In both cases, that's sufficient. It also has a USB controller built in. Same thing with the 18 mega part. And it's also programmable with Arduino. So I myself am not an embedded software engineer. So if I plan on actually implementing this with software, then this just makes my life a little bit easier for prototyping. And then finally, it has a 32-bit ARM core, which also means that, if we want to migrate to a different ARM core in the future, that's also 32-bit, that would be easy. But also it, gives us 32 bits of data to work with for our, different variables or different data types that we're going to be using. Meanwhile, the 18 mega 32U4 is actually an 8-bit microcontroller. And in this case, whether this is an AVR core or an ARM core isn't really a pro or con. This might come down to, your personal preference, or maybe you're looking towards the future for upgradability. Now, the RP2040 doesn't come without its cons. It actually requires an external flash for the program memory and doesn't have an EEPROM built in. So if we want to save any settings on this microcontroller, right, or if we want to save our program, we do need to have a separate chip, an external flash where that gets stored. It also requires an external clock source. So that just means that this cost of 70 cents for the actual RP2040 microcontroller is in reality a little higher because we need to include the program memory and we also need an external clock. Now again, the price of both of those might vary, but just keep that in mind when you're considering between the two microcontrollers. And then finally, it runs on a 1.2 volt to 3.2 volt supply. And I have this in the con list because the 18 mega 32U4 can actually run on up to 5.5 volt supply. So in reality, if you wanted to, you could run the 18 mega 32U4 without a regulator between the USB power and the actual microcontroller. That also means that when we're talking about the digital signals that are going to, for example, our LEDs, the IO expander, the LCD, those can all run at 5 volt logic rather than 3.3 volt logic. And then if something like, for example, the LED modules require 5 volt logic in order to function, then we won't need a logic level shifter. Now, just really quickly finishing up with the pros and cons for the 18 mega 32U4. So 26 GPIO, programmable with Arduino as well. It has built-in flash and EEPROM, so we don't need those external components, as well as an internal oscillator, but it only runs at up to, I believe, 16 megahertz, which, believe it or not, for a keyboard is actually plenty of speed, of execution speed. However, if we want to do anything fancy, like in the case of our project, we're adding a calculator, getting that 133 megahertz can be really tempting, right? So same thing, it has a built-in USB controller. And then finally, it actually has a pretty high cost of $5.26. So this $5.26 actually exceeds, the cost of this RP2040 part, plus the external flash, plus the external clock source. And then just a couple other factors like the faster clock, a little bit more GPIO, 32-bit ARM core, means that, if we go back to this block diagram, we're actually going to be using this RP2040 to design our custom mechanical keyboard. So hopefully that gave you guys an idea of how we are going to organize this project. In the next video, we'll get started by actually placing the RP2040 part and starting to connect some of the peripheral components, such as the capacitors, the decoupling capacitors, the flash memory for programming, the external oscillator, and then we'll start worrying about the GPIO probably in a future video once we start connecting the keys to it. All right, guys, that's it For this video, thank you for watching. If you have any questions, comments, or concerns, please leave a comment below, and I will see you in the next video.